In this section of Chapter 9, we're going to talk about the process of effusion and diffusion. And we're going to define both of those quantities and relate them back to some relevant gas properties. Diffusion is defined as a process that occurs when gas molecules disperse evenly throughout a container. So if I have two gases in this sealed container here, they will eventually diffuse throughout that whole container and sort of be like a homogeneous mixture. Effusion occurs when a gas passes through an opening that is smaller than the mean free path of the molecules, that is, the average distance traveled between collisions. Effectively, this means that only one particle can pass through that hole at a time. So let's say I have gas molecules over here, and I have the same volume container, but I put in a dividing plate between them. And in this case, the gas molecules got to pass through there one at a time. And different gas molecules will diffuse at different rates. So I'm going to eventually set up a concentration gradient here where I might have one higher concentration of one gas on this side than on the other side. Whereas diffusion, I have an equal concentration throughout the whole vessel. So the rate of diffusion is actually equal to the amount of gas passing through an area per unit time. So how long does it take to get this blue molecule from the bottom up to the top? So it's gas passing through that area in a unit of time. Effusion, we can actually relate to proportionality, which is equal to 1 divided by the root mean square of the mass of the particles. So I actually have to know how much each of these particles actually weigh themselves. So I need to measure the mass. Let's look at that equation in a little more detail. So diffusion involves unrestricted dispersal of molecules through space due to random motion. So if I have two molecules and I have a big opening between those two, and I literally allow the gases to diffuse between those two, eventually I open up the stopcock, I start to have the white molecules diffuse this way, the red molecules diffuse this way. After enough time, I get an even distribution of all the molecules in both sides of them. So after a short time, if these two gases were oxygen and hydrogen, I have them evenly distributed on both sides of the vessel. So here is an example using Graham's law of effusion. I have two balloons, and they're inflated with different gases, helium and argon. Let's predict which balloon will deflate first using Graham's law of effusion. So why would they even deflate? That's because these plastic balloons actually have very small holes in them that some of the gas can actually leave through. And so we know that the effusion rate of A divided by the effusion rate of B is inversely proportional to the square root mass of B gas divided by the square root mass of A mass. So we can just set up Graham's equation for these two balloons here and these two gases. So in this case, I know the molecular mass of argon is actually 40 grams per mole. The molecular mass for helium is 4 grams per mole. Set up their relationship. So the rate of effusion of helium is actually 3.16 times as fast as it is for the effusion rate of argon. You can see here, if I wait long enough, the helium balloon is actually smaller because its rate of effusion through the small sort of pin-like holes in the plastic, it effuses faster than argon, which is a more massive molecule.